Welcome to the 2020 edition of the ACM Symposium on Principles of Distributed Computing. My name is Matthieu Perrin, and I will present you a joint work with Achour Mostéfaoui and Grégoire Bonin. In 1962, Dijkstra introduced the semaphore as a useful tool to solve the mutual exclusion problem. He also advocated for the introduction of a new hardware instruction that he called nullify, but we now call test and set. Test and set is a key component for the spin-lock algorithm and efficient implementation of his semaphore. Dijkstra also noticed that this test and set instruction could be implemented using semaphores. Indeed, by disabling the concurrency momentarily, it is possible to implement any data structure with a sequential specification, be it a counter, a stack, the map of a multiplayer game, and so on. In other words, semaphores, and therefore test and sets, are universal. The use of locks is not perfect though. When two processes want to access the operation of a data structure at the same time, one has to wait for the other to complete its operations before it is able to start its own operation. If the first process crashes, then the second one remains blocked forever. In the subsequent decades, researchers have focused on wait-free data structures. No matter the relative speed of different processes, no matter the crashes, the operations performed by non-crashing processes must terminate. Lock-based algorithms cannot be wait-free, and new special instructions were proposed to implement wait-free data structures. Those include fetch and add, compare and swap, load league, store conditional, and so on. As more and more special instructions were introduced, it became clear that they could not be all included into processes, and the question of how to compare them became more and more relevant. Hurley brought an answer in his seminal 1995 paper by introducing the wait-free hierarchy. An object has consensus number x if it is universal for wait freedom in a system composed of x asynchronous processes, but not universal in a system composed of x plus 1 asynchronous processes. An object that is wait-free universal for any number of processes has an infinite consensus number. An object with a higher consensus number cannot be implemented using only read-write registers and instances of an object of lower consensus number. These last decades, parallelism in multi-core computers has been abstracted by a notion of threads that can be started dynamically at any time during an execution. Although the number of threads at each time is finite, there is no bound on the number of threads that can participate in a long-running execution. Another specificity of multi-threaded systems must be taken into account. Threads share a common memory space in which they can allocate a virtually unbounded, but finite, number of memory locations to instantiate record data structures or finite arrays. In particular, when no bound is known on the number of threads in an execution, assigning one register to each of them is not trivial. These two aspects have an important impact on which algorithms can be implemented in multi-threaded systems and which cannot, and therefore on the coordination power of shared objects. Indeed, Affec, Morrison, and Wertheim already exhibited an object called the iterator stack that has an infinite consensus number but cannot be used to implement consensus when infinitely many processes may join over time an execution. In this talk, we answer the following question: how to compare the synchronization power of shared objects in multi-threaded systems. Following the same approach as Hurley, we propose to compare the synchronization power of shared objects based on the maximal number of processes that they are able to synchronize, including in situations where the set of participating processes is initially unknown or may change during an execution. More precisely, we differentiate computing models on restrictions on process arrivals, as introduced by Gaffney, Merritt, and Taubenfeld in 2001. These models are composed of a set of asynchronous processes that may join, get started, and crash or leave during a given execution. 4 arrival models are distinguished. M1n is a classical model where the number n of processes is fixed and may appear in the code. M1 is a bounded arrival model in which at most n processes may participate, where n is only known to the processes at the beginning of each execution, but may vary from one execution to another. Intuitively, an algorithm in M1 may require the maximal number of participating processes to be passed as an argument to its constructor at initialization. M2 is a finite arrival model, in which a finite number of processes participate in each execution. In other words, after some time, no more process may join an execution. It means that an algorithm in model M2 may be forced to restart its whole execution each time a new thread joins the execution, and only provides liveness guarantees after all threads have arrived. Finally, M3 is an infinite arrival model, where new processes may keep arriving during the whole execution. Let's note that, at any time, the number of processes that have already joined the system is finite, but this number can grow indefinitely. Hence, in a multi-threaded system, an object that is universal in the infinite arrival model cannot be implemented using any number of shared registers and shared objects that are universal in the finite arrival model, but not in the infinite arrival model. Those are themselves stronger than objects universal in the bounded arrival model, but not in the finite arrival model. Finally, all the other objects have a finite consensus number in the weight-free hierarchy and can be compared by the maximal bound on the number of processes for which they are universal. As advocated earlier, the impossibility to allocate infinite arrays is an important limiting factor that restricts the computing power of some objects in multi-threaded systems. We also study the synchronization power of shared objects according to the possibility or not to allocate infinite arrays. Hence, we propose a two-dimensional hierarchy where shared objects are sorted horizontally based on their universality in models M1n, M1, M2 and M3, when infinite memory allocation is not available, and vertically on their ability to do so when it is possible to allocate infinite arrays. The stronger an object is, the more on the top, on the right, it is. An object is universal in the multi-threaded model if and only if it is in the topmost and rightmost degree. Notice, however, that the hierarchy is not strict. For example, it is impossible to implement objects in the blue degree using only read-write registers and objects in the yellow degree, because such an algorithm would require that processes stop arriving even when infinite arrays are available. On the other hand, it is impossible to implement an object in the yellow degree using objects from the blue degree, because doing so would require infinite arrays. In the remainder of this talk, I will challenge the significance of the hierarchy by exploring whether or not there exists an object filling each possible degree. Some degrees are simpler than others. First, notice that infinite arrays are never detrimental. If an object is universal without infinite memory allocation, it is still universal when infinite arrays are available. This results in the emptiness of all degrees at the bottom and right of the diagonal. Secondly, we proved at DISC 2019 that multi-valued consensus was still universal in multi-threaded systems, and therefore so is comparent swap. The difficult part was to allocate one register per process for them to announce their help requiring operations. Thanks to this result, we can regard universality as the same as the ability to solve consensus as we are used to. Rephrasing the arguments developed by Affec, Morrison and Wertheim, we can also place the iterator stack in the hierarchy. It is universal in the finite arrival model, but not in the infinite arrival model, regardless memory allocation. The part of the weight-free hierarchy containing the objects with a finite consensus number lies on the leftmost column. The original paper by Early, however, mentions no limitation that could arise in computing models when finite memory allocation is not available. One of our contributions is the proof that, in the context of bounded arrival models, infinite memory allocation is not a decisive factor to determine if universality can be achieved or not. This observation is of crucial importance, as it implies that our hierarchy coincides with the one proposed by Hurley for objects with finite consensus numbers. This is why we keep the same term, consensus number, to categorize shared objects in our hierarchy. On the other hand, we refine the class of objects with an infinite consensus number by saying that an object has consensus number infinite x, y, if mx is the most general model in which it is universal when infinite arrays are not available, and my is the most general model with infinite memory allocation. To get an insight of why this is true, let's consider an object O that is universal in the bounded arrival model with an infinite memory allocation mechanism. In particular, it can be used in a binary consensus algorithm, which is one where only values 0 and 1 can be proposed and decided. An entry of the problem is composed of the identity of at most n processes that can be bounded thanks to adaptive renaming algorithms, and one Boolean proposed value for each of them. In other words, there is a bounded number of possible entries. For each of them, termination of the algorithm implies that a finite number of configurations can be reached in any execution, resulting in a bound on the number of memory locations that can be accessed by the algorithm. In other words, the same algorithm can be rewritten without using infinite arrays. As binary consensus is universal in the bounded arrival model without infinite memory allocation, so is our base object O. Notice, however, that this argument is only correct for universality and does not imply that the models are equivalent in general. Let's now focus on objects with an infinite consensus number. By definition, even the weakest of them are universal in the bounded arrival model, and, as we just proved, it does not matter if an infinite memory allocation is available or not. As I will now prove, adding infinite arrays, however, is sufficient to solve consensus in the finite arrival model. In other words, no object has consensus number infinite 1, 1. We prove that by providing a round-based algorithm such that at round k, only processes with an identifier smaller than k can access a k consensus object, while the other processes simply announce their presence by marking a Boolean register. If the former decide first, they return the value they decided. Otherwise, if the latter arrive before consensus took place, they force more rounds to happen. If the two groups write concurrently, it is possible that some processes decide a value at round k, while others start round k plus 1. In that case, the protocol ensures that they adopt the decided value for the next round, ensuring agreement. In the finite arrival model, we know that a process with maximal identifier eventually arrives, which defines a maximal number of rounds and ensures termination. Let's now turn our attention to objects with consensus number infinite 1, 2. As we shall see now, those do exist. They are the weakest objects that can be used to solve consensus between n processes for all n. A natural object to fill this degree is a window register. A window register of size k has two operations. A write operation that takes an integer argument and returns no value, and a read operation that returns the ordered list of the k last values written. Here, we consider the generalization in which window registers of any size are accessible. The size k is passed as an argument to the constructor. It is known that window registers of size k have consensus number k, so their generalization have at least a consensus number infinite 1, 2. We still have to prove that its consensus number is not greater. That is, that it cannot be used to solve consensus in the infinite arrival model, and that it requires infinite arrays to solve consensus in the finite arrival model. The first proof relies on the classical valency argument. Let's take an alleged consensus algorithm in the infinite arrival model, and let's consider two processes attempting to reach an agreement. As usual, we can lead them to a critical configuration in which they are both about to write in the same window register of size at least 2. For the sake of argument, let's say this size is 5. As we are in the infinite arrival model, we can make 4 new processes arrive. But now we have 6 processes, and the window register of size 5 is no more sufficient for a critical configuration. The 2 first processes must do their right, and then we can lead them to another critical configuration where they are all about to write in a window register of size at least 6. The situation is similar to the previous one, but the first processes took more steps. We can repeat the same strategy over and over again, preventing termination of the algorithm. The second proof is based on a complexity argument. Hélène, Gelashvili, Shavit and Shu proved that around n over k window registers are necessary to solve obstruction-free consensus. It means that an unbounded number of window registers must be allocated by any algorithm in the infinite arrival model. Building on this proof, we also show that this allocation cannot take place dynamically at runtime. This leads to the natural conclusion that an infinite array must be allocated at the initialization of the algorithm. Actually, our proof is more general, as it also considers binary consensus as a base object. Surprisingly, this means that binary consensus is not universal in the finite arrival model without infinite memory allocation. On the other hand, multi-valued consensus can be implemented using an infinite array of binary consensus objects in the infinite arrival model. Consequently, binary consensus has consensus number infinite 1, 3. The last remaining degree to explore contains objects of consensus number infinite 2, 3. As objects of consensus number infinite 1, 3 are universal in the infinite arrival model enriched with infinite arrays, and objects of consensus number infinite 2, 2 are universal in the finite arrival model, the composition can only have consensus number infinite 2, 3 or infinite 3, 3. Indeed, we proved that the composition of binary consensus objects and iterator stacks have consensus number infinite 2, 3. The proof that it is not universal in the multi-threaded model is our most technical contribution, since it must combine valency argument and complexity arguments. The result holds nevertheless, which concludes our exhaustive exploration. To sum up, we extended the existing weight tree hierarchy by separating objects with an infinite consensus number into 5 novel categories, depending on their universality in the bounded, finite, or infinite arrival models, as well as the need, or not, for an infinite memory allocation mechanism. I would like to conclude this talk with 2 new open problems. The first one is the relevance of the impossibility result concerning binary consensus. Indeed, k-binary consensus objects are sufficient to synchronize 2 to the k processes. In any practical application, allocating 32 or 64 memory locations for binary consensus would be more than enough to synchronize all the threads that could ever be created. An interesting open question is the existence of an object with consensus number infinite 1, 3 that does not allow a polylogarithmic implementation of consensus. The second open issue is the identification of simpler objects for each degree of the hierarchy, and possibly even of special instructions that operate on a single memory location. This issue is particularly relevant for the infinite 2, 3 degree, where we only know a composition of 2 objects. This raises 2 questions. Does there exist an object of consensus number infinite 2, 3 that is not a composition of an object with consensus number infinite 1, 3 and an object of consensus number 2, 2? And conversely, does there exist such compositions with consensus number infinite 3, 3? Thank you for your attention. I have been Matthieu Perrin, and this talk was part of the PODC 2020 virtual conference.